Another special case of motion in 2 and 3 dimensions that we want to consider as part of this chapter is the case of what's called uniform circular motion. The most important aspect about circular motion is, since the direction of motion is changing, as we're exploring motion in 2 and 3 dimensions in this chapter, uh, another special case we want to consider is the case of uniform circular motion, meaning that we have an object like a ball on a string or the moon orbiting the earth. We have an object that is moving in a circle. So that part alone tells us that the distance from the point that is rotating about, the axis of rotation, to the point where the object is fixed. The position vector is clearly changing as the object is undergoing its circular motion, but the distance away from the rotation axis is not changing. So the path is a circle. The velocity is always tangent to the circle. The velocity vector is tangent to the path. So anywhere along the circle, I can put down a velocity vector tangent to the circle. And the main point that we want to get out of this is that velocity vector is changing in a particular way. Velocity vector is changing due to an acceleration, and the acceleration is only in towards the center of the circle. Some textbooks will refer to this as the radial acceleration because it's in the inward radial direction. The more typical term is that this is the centripetal acceleration, where centripetal means center seeking. So the trajectory is simple. It's a circle. So you're a constant distance from a point. The velocity vector, the length is fixed. So the speed is constant, but the direction is changing at a constant rate. And that constant rate of change of the velocity means that there is an acceleration that has the same magnitude always, but it's just changing the direction. And so at any point for an object in uniform circular motion, the velocity vector is tangent to the circle, the acceleration vector is perpendicular to the velocity, so it's in towards the center of the circle. And the uniform and uniform circular motion is telling us that this acceleration vector has no component along the velocity vector and no component in the opposite direction. So that acceleration can neither speed up the particle or slow the particle down. This acceleration is perpendicular to the velocity, and all it can do is change the direction of motion. So the phrase uniform circular motion is one of those special phrases in physics. Whenever someone says uniform circular motion, it means the following things are true. The path is a circle, so it is a path of constant radius. The speed cannot change. The velocity changes because the direction of motion is changing. The speed is constant. The acceleration always points radially inward to the center of the circle. It is the center seeking, or centripetal acceleration, and that magnitude of the acceleration is constant. All right, so the speed is constant. You're going to go the circumference of the circle in the period of the motion. So the speed is 2 pi r over the period. And then I have a separate little video to show the derivation of this, not too hard, that center seeking or centripetal acceleration is v squared over r. So if an object is undergoing uniform circular motion, there has to be a force present to provide this centripetal acceleration. And it's going to be v squared over r in magnitude. All right, let's do some questions together. A couple of them for you. So I have a ball is being whirled at the end of a string, and it's in a horizontal circle, constant radius r at a constant speed v. By which one of the following means can the centripetal acceleration of the ball be increased by a factor of 2? So read through those options. Which one do you think is correct? Confer with your physics friend, and then we'll come back together after you unpause the video. All right, so the one that will work is v squared over r. If I want to increase by a factor of 2 this triple acceleration, I can do that by keeping the speed fixed but decrease the radius by a factor of 2. That's the only one out of those 5 options that will work. Increasing the period means you go slower. Radius fixed and decrease the, increase the period means, right. Increase the period means it's going slower. So the centripetal acceleration is even smaller. Keeping the radius fixed and decrease the period by a factor of 2. So now it's going faster, but I've doubled the speed and it goes as v squared. So that's 4 times the centripetal acceleration we originally had. And we only wanted to increase it by a factor of 2. Keep the speed fixed and increase the radius by a factor of 2. That decreases the centripetal acceleration because it's v squared over r. And then keep the radius fixed and increase the speed by a factor of 2. I've already tried to do that by decreasing the period by a factor of 2. That doesn't work. So only D. All right, and have you guys try calculation. So Earth is in orbit around the sun. Hopefully that's not controversial in your mind. Geocentrism has passed. So Earth is orbiting the sun, orbit that is very narrowly circular, and the average radius is 1.50 times 10 to the 11th meters. If we assume that the Earth is in uniform circular motion for ease of calculation, what is the centripetal acceleration of the Earth in its orbit around the sun? And then a number that is going to help you in your calculation of the centripetal acceleration is that a year is approximately pi times 10 to the 7 seconds, which is a handy number to keep in mind for some things astronomical. So 1 year, and it's not exactly, but it is close enough for at least calculations like this. 1 year is approximately pi times 10 to the 7th power seconds. So you have a period for our orbit around the sun. You're given the radius. Try to work out what the acceleration is. Once you've worked it out, confer with your physics friends, and then see if you've come to the same answer. Okay. The answer for our annual motion around the sun, our revolution, it's about 6 times 10 to the minus 3 meters per second squared. And that's coming from v squared over r. V is the circumference over the period, and then you also have the radius. So you can put it all together in one grand equation, and it works out to be fairly small compared to acceleration due to Earth's gravity.